Hello. I just want to do a few problems from section 11.2. Start with number 17. The directions say determine whether the geometric series is convergent or divergent. If it is convergent, find its sum. So we're told that this is a geometric series. So let's write down what a generic geometric series looks like. It's a r to the n minus 1, n equals 1 to infinity. And this converges when the absolute value of r is less than 1, so in other words it's a fraction. It could be a negative fraction. Negative 2/3 fits this description. And it diverges when absolute value of r is greater than or equal to 1. So what we're looking to do is rewrite this formula here in this form so that we can see whether it converges or not. When I look at this, I notice a couple of things right away. It alternates, going between positive and negative, starting with a positive. I need to incorporate that into my formula. And I also notice that in the numerator I've got some powers of 4, 4 to the first, 4 squared, 4 to the third, and in the bottom, the denominator, I've got some powers of 3. Here's 3 to the first and 3 to the second. So if I'm going to establish a pattern, I'm going to start by looking at those exponents. So I'm going to first write this. Let's write the ones that are easy. This one's 4 squared over 3 to the first. And then I have 4 cubed over 3 squared. So if this is to have any kind of predictable pattern, I see the powers going down by 1 here. Let's hope that the next one, if I just follow that pattern, it equals 4. Okay, so I'm going to reduce the power by 1, that's 4 to the first, and I'm going to reduce the power of 3 to 3 to the 0, and in fact that is 4. Let's do the same. Let's reduce the power of 4 by 1, that gives me a 1 there, and then reduce the power of 3 by 1, that gives me 3 to the negative 1. And in fact, this term, even though it's a little awkward to look at, it does in fact equal 3. So I've established the pattern here. I also want to include the plus minus. So let's get this started. Let's have a negative 1 to the n power. And we're going to start with n equals 1 because I want to match the geometric series. And let's make sure this starts with a positive number. So if I plug in n equals 1, I'll get negative 1 to the first power. That's actually negative. And I want to start with a positive, so I'm going to subtract 1 here so that I match that up. I'm also choosing to do n minus 1 so that I can match up with this n minus 1. So you might be thinking, well, why didn't you do n plus 1 or something like that? Well, I could have, but I want to match that, so I'll do n minus 1. Okay, so that gets us started on a plus minus pattern. Now let's take care of the powers. I've got 4. I want to make sure it starts with 4 to the 0, so I need to start with 4 to the n minus 1. And the 3 can't have the same exponent. When I plug in negative 1 here for n, I need to get negative 1 for my first term, so let's start off with n minus 2. Now a little bit more work to do here. I want to get it in this form, so what I'd like to have is a series from 1 to infinity, and I'll have some fraction here to the n minus 1, and then some constant out in front. Now how am I going to get that? Well, I'd like these exponents to all match up. Then I could put them all in one term. So I see this 3 is the odd man out, so I'm going to multiply 3 top and bottom here. That makes this become 3 to the n minus 1. So now every term here, and there's an extra 3 up here, but this 3 gets incorporated and it becomes 3 to the n minus 1. So this whole thing is negative 4/3 to the n minus 1. I still have that extra 3 out in front. And so now that's exactly the form of the geometric series, where r now is equal to negative 4/3, and the absolute value of r is equal to 4/3, which is greater than or equal to 1, so this diverges. Let's look at number 18. It's pretty similar. Actually, this one's a little easier because it doesn't have the alternating part. Here we have 4 plus 3 plus 9 over 4 plus 27 over 16. And we're told this is a geometric series. So we should start looking to write it in terms of A, R, n minus 1. Okay, so I see again powers. I see powers of 3 on the top. I see powers of 4 on the bottom. Let's see if we can establish the pattern here. Working backwards here, let's start with this. This is 3 cubed over 4 squared. And then that's 3 squared over 4 to the first. I see that we're lowering the exponent by 1. Let's continue that pattern. 3 to the first over 4 to the 0. And then continue down to 3 to the 0 over 4 to the negative 1. So that same little trick happened in this problem here where we write it in this awkward way. But you see, we can tell exactly what the pattern is now. So this, if I want to write this in the sigma notation, it's n equals 1 to infinity. I want to start with 3 to the n minus 1 so that I get 3 to the 0, and I better have 4 to the n minus 2, because when I plug in n equals 1, the very first term needs to be a negative 1 there. And let's, I'd like for this to be a fractional power to the n minus 1. So let's modify the bottom here by multiplying by 4, multiply by 4 on the top as well. Actually, it might look a little better if I multiply on the bottom over here and on the top over there. Okay, so what do I get from doing that? I still have the 4 out in front, this 4, but the 3 to the n minus 1 is now over 4 to the n minus 1. Okay, and then one extra little step here to rewrite it as that. Okay, so that's definitely a geometric series. We have r equals 3/4. Absolute value of r is less than 1, so this converges. Now the problem asks us to find the sum, so let's find the sum. The sum of a geometric series, let's go back here, this sum is equal to a over 1 minus r. That's the formula, so if you know a and you know that r is less than 1, it will converge to this value. So in our case, we have a is equal to 4, and r is equal to 3/4. So a over 1 minus r is equal to 4 over 1 minus 3/4, which is 4 over 1/4, which is 16. So there's your sum. It converges because we have written it in that form. We can see that, and there's the actual sum. So let's keep going here. Number 23. Number 23, this is kind of a typical geometric series. I have negative 3 to the n minus 1 over 4 to the n. So remember that the geometric series has n minus 1 in it, so what I'd like to do is change that 4 to n minus 1. Then I can incorporate them with the same exponent. So let's do that. What I want to do is peel off 1 4 out of here. I have negative 3 to the n minus 1. On the bottom I'll have 4 times 4 to the n minus 1. Just peel off one of them, and now it has the same exponent as the numerator. Rewrite that one more time. I have 1/4 on the outside, and on the inside, or on the inside of those parentheses here, I can write negative 3/4 to the n minus 1. So now that's exactly in the form of the geometric series. So I can say that this converges because I can see that r here is a fraction less than 1. The absolute value of it is less than 1. And so this converges to 1/4 over 1 minus negative 3/4. Okay, that's a over 1 minus r, where a equals 1/4 and r is equal to negative 3/4. Okay, so I just put those in that formula, and I get 1/4 over, now it's 1 plus 3/4, so that's 7/4, so this is equal to 1/7. look at number 22. It's 10 to the n over negative 9 to the n minus 1, n equals 1 to infinity. Okay, so I'm kind of thinking that this is looking like 10 over 9, which is bigger than 1. I'm kind of thinking this is divergent, but what I want to do is get it in the form where this has an n minus 1 exponent. Alright, so let's just take a step here to rewrite it as 10 times 10 to the n minus 1 over negative 9 to the n minus 1. And now I see two n minus 1 exponents. Let's put those together in one fraction. This is 10 times 10 ninths, negative 10 ninths, to the n minus 1. Okay, but r is equal to, absolute value of r is equal to absolute value of negative 10 ninths, which is 10 ninths, which is bigger than 1. And so it diverges.